as I said, complex numbers are isomorphic to R2 as a vector space, but they have other properties. For instance, what we can do is we can also multiply complex numbers together, something that we don't usually do with regular vectors. Well, we do have a scalar dot product, but that's not what I'm talking about. In this situation, what we do when we multiply two complex numbers together is we again use usual algebra. We just FOIL that expression. What do we come up with? Well, we come up with AC plus ADI plus BCI plus BDI squared. Alright, AD and BC can be factored out of I to make up the imaginary part. And remember, how much is I squared? Well, I squared is just -1. And therefore, BD with a negative in front can be put together with AC to make up the real part. So altogether, the product of these two complex numbers turns out to be the other complex number, the new complex number, given by AC minus BD plus AD plus BC times I. Now, here is another connection with linear algebra. We can represent this product in linear algebra style, because notice that each one of those two quantities in bracket can be represented through 2 by 2 determinants. In fact, I can say that A plus BI times C plus DI is going to be equal to the determinant ABDC. Think about it in your own head. Is that AC minus BD? Oh, of course it is. Plus the determinant AB minus CD times I. And again, you may want to think in your own mind whether that's correct. That shouldn't take long. So again, this is perfectly equivalent to the previous formula. It's just given in linear algebra form and giving you, if you want, another use for determinants. Now, this is not an inner product. Now, remember that I just mentioned a minute ago the fact that with real vectors, vectors in R2, we can multiply them together through the dot product. And the dot product is a special case of an inner product. So you may want to ask, is this an inner product? And the answer fairly simply is no. Can you think of why? Give you one more second. Alright, I hope you got it right. The output is not a scalar. Remember, the key characteristic of an inner product is that you take two vectors, multiply them together, and you get a scalar. But in this case, we're taking two vectors, multiply them together, get another vector. So this is, if you want, more along the line of cross products, although it's not the same thing, don't get me wrong, but it's more along the line of that one rather than of an inner product. Here is something else that we can do with complex numbers that again should be fairly familiar and turns out to be quite useful, and that's the idea of getting complex conjugate numbers. And the idea is sort of like what we had when we used conjugate numbers with square roots, right? So the conjugate of a complex number a plus bi is simply the number obtained by changing the sign of the imaginary part. So it's going to be z bar, that's the notation for the conjugate, equal a minus bi. So that's the idea, and we're going to see in a minute what we can do with that. Well, one of the many things that can be done with it, one introductory thing. In order to introduce this application, I'm going to give you another definition. I'm going to define the modulus of a complex number. And the formula is going to look fairly familiar. So the modulus of a complex number, which we're going to denote by the single bars, so sort of like an absolute value. So it's sort of like a magnitude, right? Yeah, so you shouldn't be surprised by the fact that the definition is square root of a squared plus b squared. Yes, that's the same definition that we have used in R2 for the norm of a vector. So this is the modulus of a complex number. Basically tells you how big that number is by taking the square of both the real and the imaginary coefficients and adding them together and taking the square root. Okay, now notice that we can do a really neat thing by using conjugates and linking them to the modulus. Because if I multiply z and its own conjugate, what do I end up with? Well, I end up with a times a, which is a squared, then minus abi plus abi, and those cancel as they normally do in algebra, and then we're left with minus b squared I squared. But how much is I squared? I squared is -1. Which cancel the existing -1 and leaves us simply a squared plus b squared. So what that means is that the modulus of a complex number is going to be given by the square root of the product of the number with its conjugate. Okay? Now you may wonder if multiplication by the conjugate is actually an inner product, right? Because it satisfies at least some of the properties of a regular inner product, right? It can be used to figure out the norm of the vector. It is always positive for any complex number except for 0, and so on. So I'm going to leave that to you as an exercise to go through the axioms of an inner product and see if we can use multiplication by the conjugate as an inner product. Okay, so I'm not going to tell you if it is or if it's not. We may discuss that in class. Hopefully we will. Now, another use of this conjugate is the fact that we can actually divide complex numbers. Now, this may look like an obvious thing. Well, we can divide numbers. Why can't we divide complex numbers? Well, because remember, complex numbers are not real numbers, and so we have to be careful about how do we do that. So can we actually, what does it mean to divide one complex number by another? Can we actually do that? Can we even do it, for instance, with vectors? Dividing vectors or dividing matrices is something that we have seen cannot really be done. So what about complex numbers? It turns out that it can be done, of course, as long as we're not dividing by 0, by using properties of this conjugate. And it goes like this. Let's say that we want to divide a complex number z by another complex number w. And here is a situation where we need a different letter, so we're going to use a letter nearby like w. An alternative would be to use Z1 and Z2, but I know that you guys don't like that. So let's use just Z and W. Now what I'm going to do is, like in regular algebra, I'm going to multiply top and bottom by the same number, that number being W bar, the conjugate of W. So what happens? In the denominator, W times W bar, or the conjugate, is now a real quantity, because remember, that just gives us the square of the length of, or the modulus of the complex number. That's a real number. If you look back at the definition of the modulus, it's a real number, right? There's nothing wrong with it. And so what I can do is I can use that one as just a coefficient 1 over modulus of W squared, and I can put that in front of, well, in front of what? In front of the product of Z and the conjugate of W. And of course, that now I'm back to multiplying two complex numbers, which we know how to do, and so therefore this whole expression now makes sense. It can be used as a definition for the division of two complex numbers.